Got another little Bluetooth module, this one with a 50 watt amplifier that I got from IC Station. We're going to set this one up. We'll take a look at the circuit using my digital microscope and maybe do a bit of a deep dive into how the Class D system works and why it works, how we get the audio out of that PWM signal.
I put up a new studio light. Actually, I had this before, I just haven't used it in a while. This should give me a little bit of extra light right over my shoulder. This is an HMI type light. As you can see, it's warming up, getting up to temperature here. That's why you see some shadows now on my bench, because I got a very strong backlight shining over my shoulders to both aid in me seeing what I'm doing and just gives more light for the camera, as opposed to everything being lit from directly overhead. This is a 50 watt per channel module. This is from IC Station. It's a GY18048 module. Actually, this is more than a module. This is like a full little kit, little Bluetooth board here. We'll go over the specifications on this thing in a minute. So the specifications on this, it's based on a tpa3116d2. That's a Texas Instruments chip. 50 watts per channel is the maximum output power. It also features BLE 5.0. This one features bass and treble controls and their actual physical controls. So you're not having to just go through and switch. You're not having to just go through the adjustments on your phone, which is kind of nice. The power specs are as follows, and it depends on the speaker ohm or speaker impedance and the voltage. If you're using 8 ohm speakers, you get 15 watts per channel at 12 volts, 20 watts per channel at 19 volts, and 30 watts per channel at 24 volts. If you're going to be using a 4 ohm speaker, the power output is 30, 40, and 50 watts per channel, respectively, for the 3 voltages. So that's how they come up with the power rating, because the lower impedance speakers are going to pass more current, and you get, based on your input voltage, you will get more current flowing at the lower ohms. This being a Class D amplifier, everything's based on the rail-to-rail voltage switching back and forth. Here's the amplifier chip here. As you can see right now, there's no heatsink on it. We are going to be putting that heatsink on. We'll get a close-up of the chip itself so that you guys can see the construction. Actually, we can bring out the microscope. We'll take a look at the construction using the microscope before I put the heatsink on.
Okay, that's a real close-up there. I haven't raised the table up on the microscope yet, or raised up the actual camera. There's our tpa3116d2 chip and the heatsink die. This is the back of the die. Here are some of our support capacitors. And of course our output coil. Here's the regulators here. M5 350B. Our 24 megahertz oscillator crystal. That's what sets the reference for the PWM signal, which should be around 400 kilohertz. We're going to measure that a little bit later on. One of the neat things about using these microscopes is you can sometimes identify problems that might crop up down the road. Something very small that the average person might miss looking at it comes in very clear once you're able to dial it in and see a potential problem. You see what I'm getting at here, right? Looks like there's a little bit of a solder bridge here, a little ball of solder right there on C38. So I can go in here with my little pick, in this case it's a screwdriver, see if we can just dislodge that out of the way. just like that. So that's one of the things you can do when you've got an inspection microscope, is that you can go and look for any solder formed. And the board was baked and wasn't cleared out, so we can inspect the board and see. If there's any bridges. I like to check around the big chip here before the heatsink goes on, just because once the heatsink's in place, it's kind of hard to see it at that point. But everything else looks to be in order. It's looking straight down now, but yeah, everything's looking good on this board. Just that one little solder splash there. Not that it was shorting anything out, but if you can inspect the board, you can find where there may be issues. I like it. Great little microscope I got here. Okay, I think I can attach the heatsink now. You guys like my microscope? That was pretty good, eh? I can get in pretty close. I mean, I can get in close with the camera too, but that just makes it so much easier to see. And the sound on there was recorded on the microscope. If you're wondering which microscope that is, I just reviewed it about a week or so ago. So you can look that one up. If you want to see what type of quality is, it was the Star microscope. It actually works really good. I'm going to be using it. Actually, I probably shoot a video tomorrow. One of the clocks I built years ago was acting up, the LED one with the dot matrix. So I think maybe there's a connection that's gone bad on it. So we'll look at that tomorrow. I'm going to put the heatsink on right in here. So that's just done by peeling off the backing to the 3M double-sided heat transfer tape and sticking the heatsink down. There. That's all that's needed to keep that chip cool. Just press it down firmly. Going to connect up my speakers to my left and right terminals here. I'm going to give it 24 volts. Pair it with my test phone, which is this old Crackberry here. And then we'll test this out. I've got my speaker wires. I guess I can put together the rest of this cabinet for it while I'm at it. It comes with a little cover. So we'll put this together and put the knobs on it and then test it out. So this all comes as part of the kit. Even comes with a little screwdriver, which could come in handy because I believe it's a number 0 or close to it.
I'll first put the spacers in and attach the standoffs. We'll tighten these down once I get them in place. I'm starting to like this little board already, even though I haven't heard it yet, just because of the fact that it has these little standoffs to put a top and bottom on it, so nothing's going to short out. It doesn't have sides on it, but that's easy enough to build that. Still more than most of them. Most of the little boards are just that, a bare board. So we'll just tighten these down. These needle nose pliers have been missing for the past 2 or 3 years. I located them after my 22-year-old moved out, and we were cleaning out her room, and there were my there were my pliers. I guess she borrowed them and just neglected to return them, and I've been only searching high and low for them. I don't know how many times I was on the ground under my bench thinking that I dropped them and couldn't find them. Turns out they were stolen all along. And then the bottom cover. Appears to be one screw left over. Here we go, volume, bass, and treble. These are BTL or bridge tied load output, so you cannot short the speaker leads together or it will blow the amplifier, so keep that in mind. You need a full run for each speaker. I've got a plug here to plug in. Can just connect this to my power supply. I'm going to feed it 24 volts. When I turn on the power, it should beep. It did very low there. I'll give it a bit more volume here. Should be able to search and find your settings, Bluetooth. Should be a ZK502. See if I find a ZK502 device in here. It's probably this one here. Bushy? Yeah, it could be this bushy. There we go. So if I play music, actually that sounds very good. Wow, I'm more impressed. That sounds better than I thought it was going to sound. You can take a look at the waveform on this thing. You guys want to see that? We'll just take the screws back out here so I can access the chip, or access the outputs, the output coils, and we can take a look. It's just going to be a standard PWM signal, as that's what these are. These are a PWM amplifier. Nothing real fancy. They all pretty much all operate the same way. We'll look at this one on the scope. I'll use a digital scope, I think, for this one. It's a little easier to see the waveform on a digital scope than an analog scope. I'm just going to scope the output, the unfiltered output, because it'll be a square wave PWM signal at the input of each of these coils. The other side of it is filtered to the audio. So let's look at the unfiltered side. So when I first connect the scope probe, we are going to see basically a square wave signal. Let me just hit my auto, or set my set up my trigger. There we go. So what we're seeing here, we can increase the voltage here, voltage gain. What we are looking at here is we're looking at the square wave signal coming off of the IC. Turn on my, where's my, it's been so long since I've used this thing. So we're operating at 400 kilohertz, as you can see. We have 30.6 volts peak to peak. And when there's no audio, we have a nice clean square wave signal. That little peak you see there, that's just induction from the actual choke coils. As I start to put volume to it, you'll start to see the duty cycle change. It changes with the music content. The louder I turn the volume, the more swing there will be. Now, for those of you that aren't familiar with how Class D or pulse width modulation amplifiers work, the amplitude coming off of the chip always is at rail-to-rail voltage. I'm feeding it 24 volts now. If I drop my voltage down to 12 volts, you will see that the voltage will drop accordingly. Again, when I turn on the sound, easy way to think of this is your leading edge never moves. It's your trailing edge that moves. You'll notice the leading edge to each cycle remains constant. If I turn the voltage down even more, I think I can go down as low as 9 volts on this. I can probably go down even lower, but it's going to shut down. Where's it shut down? I'm at 5 volts now. Will this thing run at 5? Yeah, it will, but you see, when you drop your voltage, you get into distortion. Very easy. Increase the voltage. So, if you want to think about how these things work, think about this side, the falling edge, not the rising edge, but the falling edge. Think of that as your waveform sitting at zero volts. And as the waveform rises and falls, as the sine wave rises and falls, this edge, the trailing edge, is going to swing back and forth. In unison, this side here, in unison with the waveform. So if I were to give it a low enough frequency, you would see it just going back and forth, and the speaker cone would be following that. Now the reason we're not seeing this thing traverse back and forth, or deviate back and forth, on an analog scope this would be much harder to view because this would be spreading out at the actual audio frequency. We can actually see it better on a digital scope because we're taking a sample. So that's why it appears to be moving slow. If we were to look at this on an analog scope, which we can do. We can look at this on the analog scope just so you can see the difference. So here's the same thing on the analog scope. Watch the deviation. Of course, my music stopped playing. Now you see it, right? There's your trailing edge. And if I go to the other side of the filter, this is what we have. Neat, huh? That's how Class D amplifier operates. Now I hear people all the time, they get upset if you call a Class D amplifier a digital amplifier. They will be very quick to point out that it's not a digital amplifier, it's an analog amplifier, it's a pulse width modulation amplifier. And that is correct. It is a PWM, a pulse width modulated signal, which looks very much like a frequency modulated signal. If you were to look at an FM modulator, if you were to look at an FM signal coming off of an FM transmitter, it is going to look almost the same, except for your leading edge would not remain static. Your leading edge would actually change in frequency, because on FM, you're actually deviating the frequency. This stays at 400 kilohertz all the time, and you're just changing the actual duration of that pulse. So it's a pulse width. But it's still a digital signal. It's still a binary signal. Your output has basically, it works like a 1 and a 0, right? You've got a low and a high output, and the chip itself is generating that 400 kilohertz square wave carrier, and you're changing the duty cycle of that carrier. But it's binary. It's still 1s and 0s. It's just you're changing the duration of a 1 and a 0, and you're changing that duration of the 1 and the 0 in an analog fashion with respect to the incoming analog signal. The analog signal is sampled in the chip, so the analog signal actually goes into the chip and it's sampled in the chip. And how it's sampled is it's added to a triangle wave. So a triangle wave is this, right? Triangle wave, up, down, up, down, up, down. When you mix your analog audio signal with that triangle wave, you create yourself, and run it through a comparator, you create yourself a pulse width modulated stream, basically. That is how these things work. So in that aspect, the output is digital, because it's basically, it's either on or off. The output level does not change. It's either full rail voltage or 0. And that is filtered out by the choke and the capacitors. That is filtered out, and your audio signal restores. I hope that clears up a little bit of misunderstanding of how a Class D amplifier works. Once you understand how they work, they actually aren't that bad. They are a very efficient design, and I'm still a tube guy, okay? I still like my tubes. I like the sound of tubes. I always will like the sound of tubes. But you know what? I have to say, these actually do sound very good. I don't know how it comes over on microphone, but the harshness of the first generation Class D amplifiers didn't sound all that good, because the carrier frequency was typically around 100 kilohertz, and they found that the 400 kilohertz tends to operate very good, because there's no subharmonics that are going to get from that carrier. Even anything that could possibly leak through is still going to be so far beyond the range that your speakers ever could reproduce. It's never going to be an issue. Anyway, I'm rambling on too long about that. This was just a quick demo to show you this little amplifier board that I got from IC Station. Link to it is in the description. Thanks for watching. We will catch you in the next one real soon. Bye for now.